So thank you so much for the invitation to speak to you all today. I'm excited to share some new results from my PhD research in the Tangra Yumco Rift of South Central Tibet. This photo was actually on the cover of GSA Today in June last year. And it's one of the larger mountains within the Tangra Yumco Rift, over 6,000 meters or over 21,600 feet. So it was a great backdrop to much of our time on the plateau. See if I can move slides here. There we go. Did that work?
Yes.
Great. Okay, so why study a Tibetan rift such as the Tangra Yumco or TYC rift? To briefly sum it up, it offers a unique opportunity to investigate rift processes within a type example of continental rifting related to intercontinental collision. It also provides an ideal location in which the structures are well exposed and unconcealed by layers of sediment or water to explore outstanding questions concerning the kinematics and dynamics of young continental rifts. And finally, the TYC rift acts as an excellent field laboratory to utilize methods such as zircon, uranium, thorium, helium thermochronology to address major tectonic questions. Additionally, the study of failed or early stage continental rifts endeavors to answer many of the same critical research questions as successful continental rifts. From the evolution of extension rates through time to preferential rift geometry or short and long-term growth and evolution processes, there's much information to be gained by studying failed or early stage continental rifts. So let's dive into the discussion about Tibetan rifting. This figure shows the locations of tectonic features and major extensional structures of the Tibetan Plateau. The plateau is composed of 4 major terrains, which were accreted through a complex tectonic history, including multiple phases of ocean basin closures, creating a series of suture zones, which are shown in blue here. Oblique convergence, indicated by the white arrow, and collision of India with Asia began around 60 million years ago, shortening and thickening the crust to form the Himalayan arc and uplifting the Tibetan Plateau to an average elevation of over 5,000 meters. Arc parallel extension along generally north-south trending rifts, shown in red on this map, crosscuts the pre-Cenozoic structural grain of the plateau and is thought to have initiated synchronously during Miocene time. However, the kinematics and dynamics of extension in convergent settings are not fully understood. The yellow box in the center shows the location of the Tangra Yumco rift. We chose TYC as a field site because it's one of the longest, most centrally located rifts on the plateau. And again, it offers a unique and accessible field laboratory to test kinematic and dynamic models for rift initiation and growth. So that brings us to our research questions. How do rifts behave in contractional orogenic belts? Or specifically, how do rifts initiate and evolve through time in Tibet? This figure, modified from Curry et al. 2016, outlines 4 kinematic models for normal fault growth: tip propagation, segment linkage, constant fault length, and tectonically influenced tip propagation. Each model has specific predictions for the map pattern of fault displacement, as well as the spatial distributions of thermochronologic data. For example, model A, tip propagation, would predict ages that are oldest in the center of the fault and younger towards the tips. By analyzing spatial and temporal trends of zircon helium ages along strike of the Tangra Yumco rift, we can start to better understand how rifts might initiate and evolve in contractional settings. Secondly, what drives rifting in contractional orogenic belts? Numerous dynamic models have been proposed to explain extension of the Tibetan Plateau. I've chosen to highlight 4 classic models here: removal of dense lithosphere, lithospheric weakening, decreasing horizontal collisional stress, and India underthrusting. I don't have time to go into the specifics of each of these models, but the important thing to know is that each dynamic model also has a set of testable predictions related to the spatial and temporal distributions of zircon helium ages. For example, the India underthrusting model would suggest the presence of older zircon helium ages to the south that gradually young to the north related to underthrusting of the Indian plate. Our sampling strategy was designed to obtain a large spatial distribution of well-constrained zircon helium ages along the Tangra-Yumco rift to test both kinematic and dynamic model predictions and determine the best fit models compared to our data and structural observations. Our methods included field mapping, zircon helium thermochronology, uranium lead geochronology, and hefty thermal modeling. On the left are some photos showing the geologic mapping and sample collection process. Here's a particularly large and beautiful fault scarp with me for scale. And on the right shows the general flow of analytical methods from single crystal processes all the way through detailed thermal history modeling. I won't go again into all the details here, but we chose to use zircon helium dating in this study because it records tectonic processes that affect the upper 10 kilometers of the Earth's crust. And therefore, it's really well suited to answer questions related to rifting in Tibet. Hefty thermal modeling allows us to obtain more detailed time temperature paths for each of our samples based on different thermochronometer inputs. And that can reveal rates of cooling and exhumation and provide potential thermal histories for different portions of the Tangra-Yumco rift. I'll quickly note that this hefty model is actually from work in the Anaconda Metamorphic Core Complex in Southwest Montana that we recently published in Tectonics. So you could also give that a read if you're interested. So now on to some results. This is a neotectonic map showing active faulting and structural data that we collected from the southern Tangra-Yumco rift. Kinematic observations indicated that South TYC is composed of a series of dominantly north-northeast striking, high-angle active normal faults. Exhumed granodiorites showed pervasive northeast dipping foliation with observed slip lineations and fault plane striations suggesting northeast directed oblique sinistral normal slip, which you can see in this blown up map here in the center. We also mapped some offset quaternary alluvial fan deposits just to the west of Suruko Lake, which further evidence active faulting. This map shows our sample locations and new zircon helium ages. I'll note that this is all still a work in progress as I'm currently working to produce a detailed geologic map of the area, and ages from 25 additional samples that are still undergoing analysis will be added to the map as the data are continually received. From the data that we see here, we can start to look at the along strike trends in the zircon helium ages. From our initial results shown here in the blue box, we started to see a trend of older ages in the south and younger ages in the north, which we thought was very interesting because the India underthrusting hypothesis or India underthrusting model would predict the same older in the south and younger in the north spatial trend of ages. We recently obtained and updated the results with some more ages, filling in the gaps here in this sample map shown in this green box. And what we were starting to see is more of a concentration of Oligocene to Miocene ages near the Ganges range in the south, while to the north of the Ganges range, we can find both younger Miocene to Pliocene ages, as well as older Paleocene to Eocene ages. So another way of looking at this data to help make sense of everything is to plot date versus latitude for all samples. Here we have the zircon, uranium, thorium, helium date on the y-axis and latitude in degrees on the x-axis. You'll notice there's a distinct break in the data at around 29.8 degrees latitude, which is the approximate northern extent of the Ganges range at this longitude. We can start to see distinct groupings in the data reflecting the Oligocene Miocene ages near the Ganges range in the south, while to the north of the Ganges range, we can see these older, potentially unreset Paleocene to Eocene ages, as well as some much younger Miocene to Pliocene ages. We theorized that the southern ages could potentially be reflecting a pulse of exhumation related to the timing of uplift of the Ganges range, whereas ages outside of the Ganges range to the north could be reflecting the much younger rifting signal, even as young as 4MA, which is potentially one of the youngest ages that I've seen in my research across the Tibetan Plateau. Or potentially there may be some areas where not enough rift-related exhumation has occurred and those samples have not yet been reset. So preliminary hefty modeling was completed for each sample using the input parameters from the median grain. Our future work will include modeling multiple grains from a single sample and then multiple grains from multiple samples for each of these transects we collected.
Aislin, you have 10 minutes now.
Perfect, I think I'm doing good. So to interpret the spatial trends in these predicted thermal histories, the easiest way to compare them is by looking at the farthest south sample and the farthest north sample that have been reset. If we look at these models, we can see that the model paths begin at higher temperatures or depths in the Earth, with initial timing left relatively unconstrained by this large box to allow rift exhumation to initiate at variable times. The paths end at the surface at present day and are dominantly constrained by zircon helium age and diffusion parameters that are specific to the median grain from each sample. Looking at the trends in these time temperature paths, it appears that both samples experienced multi-phase cooling, with an initial slower phase of cooling followed by one or more phases of rapid cooling, potentially indicating the timing or acceleration of rift-related exhumation. The onset of rapid cooling in the southernmost samples has the greatest density of paths between around 22 and 18 MA, while for the northernmost sample, the onset of rapid cooling is much younger, between around 12 and 8 MA. This supports our initial observations that the onset of rapid cooling youngs to the north and is in agreement with the zircon helium results from this and previous studies. Future hefty modeling will incorporate zircon uranium lead dating to better constrain the older thermal histories, as well as apatite fission track and apatite helium dating to constrain the younger thermal histories. So based on the kinematic observations from the field, normal fault patterns from geologic mapping, and spatial trends in our zircon helium ages from this and previous studies, we interpret the best fit kinematic model to be the segment linkage model. This model predicts similar normal fault map patterns to what we see in the Tangra Yumco rift, and also allows more variability for the spatial distribution of the age of extension onset. The spatial variability that we see in our zircon helium ages could potentially be related to the timing and rates of extension along different fault segments. Additional thermochronologic data will help to expand our observations and further test this interpretation. The spatial trends of our reset zircon helium ages may indicate an older in the south and younger in the north timing of extension onset, and hefty thermal models indicated multi-stage cooling histories with a northward younging acceleration of extension rates along the TYC rift. Therefore, we interpret the best fit dynamic model to be the India underthrusting model. This model predicts that underthrusting of Indian lithosphere beneath Asia increases crustal thickness to a critical gravitational potential energy, initiating upper crustal extension during Miocene time and causing an acceleration of extension rates in the Pliocene. This model predicts that rifting is active and ongoing, with an acceleration of extension rates that tracks the leading edge of India as it propagates northward beneath Tibet. Reported bimodal volcanism in northern Tibet, north of the Bangong Suture Zone, and seismic studies imaging Indian lithosphere beneath the surface trace of the Bangong Suture Zone also provide additional supporting evidence that's independent from our zircon helium results in support of the India underthrusting hypothesis. So now for some conclusions. Zircon helium and hefty modeling results for reset samples indicated a multi-stage cooling history with the onset of rift-related rapid exhumation younging to the north. We interpret the TYC rift evolved through fault segment linkage with a northward sweeping acceleration of extension driven by underthrusting of the Indian plate beneath Tibet. This work demonstrates how zircon helium thermochronology can address major tectonic questions and outstanding problems in the field of rift research by testing kinematic and dynamic models of upper crustal extension. Prior to this work, minimal thermochronologic data was available for the Tangra Yumco rift, and upon completion, This work will contribute a robust data set of 250 zircon-helium dates in and around the Tangra-Yumco rift. I'm also completing zircon-uranium-lead, apatite fission track, and apatite helium dating to better constrain hefty thermal models. My goal is to develop a deeper understanding of the kinematics and dynamics of rifting in the Tangra-Yumco rift and broader Tibetan plateau, which can be considered a type example of continental rifting related to intercontinental collision. I'd like to quickly acknowledge the agencies that funded this research, as well as my collaborators listed and shown here. Thank you again for the opportunity to share my work with you today, and I'll be happy to answer any questions.
Thanks a lot for this great overview. Do we have some questions? If yes, please type them in the chat or raise your hands, whatever you prefer. There's one hand raised by a convener. Do we have someone else? Andrew, you go ahead.
Okay. That was a really nice talk. Thank you very much. Could you explain again the southern samples? Because I thought at one point you concluded that those 20 to 18 million-year-old ages were related to the Gandhisi thrust. And so how do you differentiate thrust-related exhumation from rift-related exhumation, given that they're happening at the same time?
That's a very good question. Yeah, and I kind of wanted to lay this out since we recently got more dates back. I wanted to lay this out showing sort of like our initial thoughts that, okay, what we're seeing is these older ages in the south and younger to the north. So what's really causing that? Is that truly just related to underthrusting of India beneath Asia, or is there something else at play here? And as we got more data, we're able to see that some of these ages just to the north of the Gangdesi range, even in close proximity to each other, some of them are not reset. They very closely match with the uranium lead ages that we are receiving, whereas others are quite young. And those are the ones that are more specifically collected from near these mapped fault scarps that we observed in the field. So really, I think that the idea behind this being more related to Gangdesi thrusting is that really we see these ages between around 28 to 16 MA isolated within the Gangdesi range. And this is true as you move to the east and west along the Gangdesi range as well. If we had a broader map to look at, there would be ages of these similar ranges all throughout the Gangdesi range. So I think that's why we're sort of thinking a little bit more along the lines that these are related to exhumation and uplift due to uplift of the Gangdesi range versus these younger ages actually reflecting rift processes.
Thanks.
Okay, Fola, you're next.
Yeah, thank you very much for that exciting presentation. So my question is, do you know if this faults root into the Moho, or are they bounded within the upper crust or within the orogenic belt itself?
That's also a very good question. I know there's a lot of different ideas of what's happening in Tibet because the crust is so thickened. A lot of people think that the lower crust is behaving more ductily in Tibet, and there's a lot of ideas of ductile extrusion tectonics that people have come up with and done a lot of research on. I think in this case, at least from what I can see, I'm really only measuring the upper 10 kilometers of the crust, which is the very brittle upper crustal portion. But there is a lot of evidence as well that at least in some places, the lower crust is involved. Just to the west of Tangra-Yumco is the Lungar Rift, and there's been a lot of work done on that as well. I think actually the opening slide from the Styron paper that you had in your introduction, Sasha, was showing a figure from that paper. And in those studies, they're studying more low angle normal faults and as well as some metamorphic core complexes in Tibetan Plateau. So I think definitely there are places where the lower crust is involved. And I'm sure there's some input or some influence from the mantle, but it isn't totally clear whether there is coupling or decoupling between those different horizons, if that answers your question.
Yeah, thank you.